Section 6.5, Theorems about roots of polynomial equations. In this section, we're going to look at three different theorems relating to finding the roots of a polynomial equation. That would be the rational root theorem, the irrational root theorem, and the imaginary root theorem. So we're going to start with the rational root theorem, which basically says that a rational number, that's where we get the P over Q, right? A rational number is any number that can be written in the form of a fraction. And it says that would be the root of a polynomial, P of x equals 0, if P would be a factor of what we call the constant, right? Remember, that's the term that we use to refer to this number here in our polynomial. And Q must be a factor of a n, which a n just simply refers to the leading coefficient. So what I'm going to do is I'm going to use the terms leading coefficient and constant. Constant is one that you're very familiar with, and I know I've used the other, but maybe not to the point where you're totally familiar with it yet. But those are the two numbers that we're going to be concerned with out of our polynomial. Those are the ones that we're going to use to help us find the rational roots of these polynomials. Okay, so let's see how this actually works when we use it. When I work with finding the rational roots of a polynomial, I want to start by making a list of my factors that I can use. So to do that, I'll start right here with my leading coefficient. If I have x cubed, my leading coefficient is going to be 1. And for the case here, my leading coefficient, those factors will be the possible values that I can use for my q, or my denominator. Well, the factors of 1 include positive 1 and negative 1. It's the only thing I can use to multiply together to make a 1. Now, if I switch that and I move on to my constant, which is an 8, those would be the factors that would give me my possible values for p. Now, 8 has quite a few more factors. We have 1, both the positive and negative. We have 2, we have 4, and we have 8. So I actually have technically 8 different things that I can use as a factor for p. And once I get those determined, what I'm going to do is I'm going to put those together, and I'm going to find all of my possible combinations of roots, which would be taking p divided by q. So I'm just going to go down my list, right? And this is a fairly easy list because the only thing I can use for q is 1. And I will start by taking my first factor here, p, dividing it by the factors of q. 1 divided by 1 is just simply going to be 1. And I continue down the list, 2 over 1, that's going to be 2. And then I go down the list again, 4 over 1. And then last, 8 over 1 is 8. Okay, so in this case I have 8 different possible roots for my polynomial. And what I want to do is I want to find out which one, or ones, there could be more than one. If you remember from previous, since this is a cubic equation up here, there's a possibility that I could have up to 3 of these. But I want to see which ones are actually rational roots, which ones would actually be part of the factors of this particular polynomial. So what I have to do to determine that, according to the theorem, is that this particular root would make the polynomial equal 0, okay, which would make it a 0 of this polynomial. So I'm going to take my polynomial and I'm going to substitute each value into this equation. So I'm going to take my 1 and I'm going to plug it in up here to this equation, and I'm going to calculate that value, and I'm going to find out what that is. Okay, well, I'm going to speed up this process a little bit. Okay, so p of 1 would be 3. If I substitute in a negative 1, that would be 5. If I do 2, I get negative 4. If I put in a negative 2 and calculate, I get negative 12. Now remember, I would be taking the time to substitute these values into the equation and calculate what they equal. That's where these numbers are coming from. I'm not just making them up here. If I substitute the value 4 into the equation and I calculate, I get 0. If I substitute my negative 4, I get negative 112. If I put 8, I get 248. And if I put negative 8 into the equation, I get negative 744. And I just tried to speed up this a little bit, but you would actually have to sit down and calculate each one of these values individually. Okay, so now that I've done that, what I'm looking for as far as a root goes is any of these that made the equation equal to 0, because that's what my equation was equal to in the first place. And the only one I find here is 4. So if I'm going to say that I have a rational root of this polynomial, it does have one rational root, which is 4. And that tells me that if I only have one rational one and there's supposed to be 3 of them, that the other ones are either going to be irrational or they're going to be imaginary. But I do know that I have one of them at least, and that's x equals 4. Okay, so once we use this theorem, we can actually use it to help us find those other additional roots. So like I said on the last example, we have one rational, which means we have to have somewhere an irrational or imaginary roots, because there's got to be a total. So like here again, it's a cubic equation. I should be having 3 roots. Whether those are rational, irrational, imaginary, I'm going to find that out here in just a minute. So I'm going to use my rational root theorem again, and it says I have to find at least one root. So I don't necessarily have to check all the values like I did last time. As long as I go until I find one of them, then once I find one, I can use my synthetic division and sort of finish up my problem from there. So let's do that. Again, we're going to find our roots. We start by finding our list of numbers for, I'm going to start with p this time. P is -1, that's my constant. And so the factors of -1 are 1 and -1. Then I'm also going to find the factors of my q, my leading coefficient, which this time happens to be 2. So that's going to be 1 and 2. And once I find those, then I simply want to find all the possible combinations of p over q. Okay, well this time this is going to work like this. So p is 1 over q, 1 over 1 is 1. And then 1 for p over 2 for q is going to be 1/2. So I don't have as many options this time. I have 4 of them, a positive 1, a negative 1, a positive 1/2, and a negative 1/2. And I'm going to calculate those. So if I take my polynomial and I put in a positive 1, I am going to get the value of 2. If I take my polynomial and substitute -1, I get -6. So far, no rational roots. Then I substitute 1/2. And I get 0. So right here, I've found one of my roots. Now, on this one, since I only have one more root left, I'm going to go ahead and calculate that. And I'm going to put in -1/2 just to see if there's another rational root. And I calculate that out, and it actually comes out to be -2.5. So I only have one rational root, which tells me that the other 2 roots are going to either be irrational or they're going to be imaginary. So let's see what we can do with that. It says to use synthetic division because that's probably the easiest and simplest way to go. So in my box for my synthetic division, since my root is 1/2, I'm going to put 1/2 right into my box and I'm going to do my synthetic division. So my coefficients are 2, -1, 2, and -1. And I'm just simply getting those from my polynomial up here, right? All my coefficients of my terms. And we're going to do this division and divide out that root or that factor that I know I have. So I bring down my 2. 1/2 times 2 is 1. -1 and 1 are 0. I take 1/2 times 0, and I get 0. So we'll put that up there. 2 and 0 make 2. And 1/2 times 2 makes 1. Gives me a remainder of 0. So what I have left as far as the factoring goes here is I have 2x plus 2. And I want to find out what makes 2x plus 2 equals 0. And since there are no more rational roots, I know this doesn't factor. So my 2 choices of solving this right now are to use quadratic formula Or in this case, because there's just simply an x squared for my variables, I could just use square roots, which is what I'm going to do. So to do that, I'm going to subtract my 2 first, and I get 2x squared equals negative 2. Then I'll divide by 2, which would give me x squared equals negative 1. And when I square root both sides, I get the square root of negative 1. Now, the square root of negative 1 is an imaginary number. It's I. So what I really end up with is plus or minus the square root of I. So remember I said how there would be 3 roots because we have a cubic equation. My 3 roots would include a positive 1/2, a positive I, and a negative I. Those are my 3 roots that I have. Okay, so what we just did, if you noticed, my imaginary roots came in a pair, right? I got positive I and I got negative I. Well, that's what the irrational root and the imaginary root theorem talk about. They talk about when you have an irrational number or an imaginary number as a root, you always have what we call the conjugate to go along with it. So if, for example, I know that a plus the square root of b is a root, automatically a minus the square root of b has to be a root of my polynomial. So down here, this is really pretty simple. If I know that 1 plus the square root of 3 is a root, then I also know that 1 minus the square root of 3 is going to have to be a root. As well as if I know the square root of negative 11 has to be a root, then I know the square root, or I should have said this, negative square root of 11, then I know that positive square root of 11 is also a root. Okay, so over here, very simple. 2 minus the square root of 7 gives me 2 plus the square root of 7, and square root of 5 gives me a negative square root of 5. Just make sure to keep that negative on the outside of your sign there. All right, so the imaginary root theorem is the same way. It says if the imaginary number a plus bi is a root, then its conjugate a minus the bi is also a root. So same thing as I did on the last one, right? 3 minus I is a root, which makes 3 plus I a root. Just like I had I and negative I. If 2i is a root, then negative 2i is a root. If 3i is a root, then negative 3i is a root. If negative 2 plus I is a root, then negative 2 minus I is a root. And it's that simple. Imaginary and irrational roots have to come in a pair, one positive and one negative.